set up, I was told to remind folks that are in here, and I'll mention this again at the end as well, in case anybody comes in afterwards, that there is a happy meeting at 5:15 this evening, and that is located here in this building as well. And I'll mention it again once I find exactly what page we have that on, so we'll be a meeting this evening. So Gary, all yours. Thank you for coming.
First, I would like to take this moment and thank Bradley Layton and Dr. Edward Larson who helped me prepare this presentation. I'd like to thank the AFE and SAFE chapters. Most importantly, I'd like to thank all of you for giving me the chance to be in front of you and present my research at the moment. But, you know, it might not really matter because some people say in 18 days the world's going to end. You know, whether it's going to be a meteorite that slides into the side of the planet or a tsunami or something. I don't know, there's many conspiracy theories, but according to NASA and empirical data, the biggest threat this planet faces at the moment is the threat of mankind destroying its natural processes. Now, these natural processes actually lead to uncontrolled amounts of heat-trapping gases being released into the atmosphere worldwide, and scientists are continuing to argue whether global warming is occurring or not. Okay, so I asked myself, if these situations are happening and they are occurring, how can we stop them and what are they caused by? Now, with the discovery of Clostridium phytophormentans, and I'm kind of rough on the pronunciation of that, but it's a soil-dwelling bacteria that eats wood pulp and excretes ethanol. Now, with that technology, biofuels are becoming more efficient. I have a question to ask all of you at the moment. How did the United States bring itself out of the Great Depression? One word, expansion. Now, the expansion of the prospective future of oil reserves and into the biofuels technology is going to expand the American economy. And I'm going to explain how that's going to happen. Now, the United States, it would give the United States an economic chance to lift itself out of the recessions and the current deficits that it's in. Now, theoretically, an ethanol-based industry would solve the problem if ethanol were the only fuel used. Now, from the transportation to the harvesting to the eventual distillation and distribution networks, if ethanol were the only fuel used, it could be a viable means to limit the amount of greenhouse gases being emitted into the atmosphere. And I'm going to talk a little bit how that could happen. Now, heat-trapping gases in the atmosphere are mainly carbon dioxide, methane, and water vapor. Without these gases in the atmosphere, the Earth's average temperature would be about -2 degrees Fahrenheit. With these gases, it's a comfy 59 degrees. CO2 is found in all living organisms. It's sort of like water. You can find it as a gas in the atmosphere. You can find it as a liquid in crude oil and dissolved in oceans. You can find it as a solid in the lithosphere as limestone, dolomite, chalk, or, as everyone knows, coal. Now, there's one important thing to understand. The Earth has 2 carbon footprints. One is man's footprint, and the other one is the natural footprint of Mother Nature. It is also important to understand that these biomasses, everything on the surface, is eventually going to decompose and release their eventual molecular composition, or their CO2s, into the atmosphere. Analysis of ice core records from Antarctica have shown us that in year 1, the parts per million of carbon dioxide in the atmosphere was 267. 1902 years later, those numbers had risen to 296, and I'm sorry you can't see that. Okay, with the advent of the Industrial Revolution and about 100 years of coal burning for electricity, last year these levels had risen to 387 parts per million. If business as usual continues and this carbon levels continue to rise in the atmosphere, in the year 2100 there will be 556 parts per million in the atmosphere. Now, this is going to correlate to an average surface temperature increase anywhere from 60 to 70 degrees Fahrenheit. Now, why does this matter? This matters because absent the presence of mankind on this planet, the Earth is still going to release carbon dioxide on large scales. Now, town gas in the 1800s was used to heat homes and light street lamps. Town gas is made by burning coal in an oxygen-free environment, scrubbing the gases of all the nasty sulfur smells, and then piping it off to the customers. Well, with the advent of electricity and then the incandescent bulb, town gas faded in time. Syngas is made with wood substances using the exact same oxygen-free environment. This process has been advanced to the point, and even incineration has been advanced to the point, that sulfurs can be eliminated in the sandbox of fluidized beds. Nitrogen dioxide can be eliminated in flue gas chambers with limestone slurry, and CO4 can be converted to CO2. Essentially, the greenhouse gas emissions out the top of the smokestack of a biomass reacting facility at this moment in time is better for the atmosphere than letting trees or biomasses rot naturally. And there's one concept that makes this entirely comprehensible. Another name for heat trapping or greenhouse gases are decomposition gases. And if global warming is occurring, it is caused by heat trapping or decomposition gases. The problem, they say, with biomass is the cost. But I know a university in Montana that's been saving around $20,000 a year in natural gas costs while shipping a fuel source of over 200 miles away. This is the University of Montana Western's tandem biogas boilers. Now, I'm going to talk a bit about the difference between burning coal and biomass woody substances for the production of mainly electricity. Creating 600 megawatts of electricity with a woody substance, biomass, releases the exact same amounts of CO2 in the atmosphere as creating 600 megawatts of electricity with coal. Now, the only difference is the biomasses are going to release their carbons into the atmosphere absent mankind on this planet, and the coal or even natural gas in most situations never would. Now, last winter, I met with Oliver Fritz, Director of Policy at the Assistant Secretary of Defense, Office of the Assistant Secretary of Defense. I met with Captain Chris Tisdale, Director of Operational Energy for the U.S. Navy, Colonel Paul Rouge, Director of Operational Energy Integration for the U.S. Army, and Kevin Geis, Deputy Secretary of Energy for the Air Force. These men give the United States 120 days to go into catastrophic meltdown if, for some reason, these shipping lanes out of the Middle East are closed. Now, the United States military, from the Air Force's Blue Angels to the Navy's Great Green Fleet to high-altitude circumnavigation of the planet, they have tested and used biofuels. They are looking for alternatives and a drop-in replacement for the fossil-based fuels, and they want large-scale manufacturing that at this moment in time does not exist. But there is a technology today that exists to use the carbon cycle to inhibit global warming by giving an economic aspect to several environmental issues. Now, I've heard a lot lately about global warming and how, if it is happening, it is caused by heat trapping or greenhouse gases. What I haven't heard a lot of are solutions. The simple economic solution, as Montana Western has come to understand, is to inhibit greenhouse gas emissions by using natural decomposition gas to create electricity. Now, I'm going to talk a bit about the modest amounts of biomass needed. Estimate the population of a small rural community, about 60,000. Now, if each resident in this community uses roughly 10 billion megajoules of energy in a day, and because the latent heat energy in wood means that it takes about 37 square centimeters to heat 1 liter of water to a boil, and that means the latent heat energy is 15 megajoules per kilogram. Now multiply those megajoules, or multiply the 10 billion joules by the 600 or 60,000 people per day, and then divide it by the 15 megajoules per kilogram of every woody substance, and it produces 4 million kilograms per day. Now this is a shipping container, 21 meters square, full of wood chips that would be used to fuel a fluid bed biomass reactor that produced electricity constantly for one full day to a community of 60,000 people. And now I'm going to take a bit and I'm going to talk about what the effects this 21 meter of wood chips would have on our forests. You might think, because it's flashy and it's in all the news, that fire is the #1 disturbance agent out there, but it's not. The #1 disturbance agents in our forests are insects and pathogens. Now, I'm going to talk a little bit about large-scale tree die-offs, but not by fire. I'm going to talk about 3 million acres of timberland killed in Alaska by the spruce beetle. I'm going to talk a bit about the pinyon nips in the southwest, and I'm going to talk about the mountain pine beetle in much of the west. Now, let's just use Alaska's 3 million acres as a reference point. That is 4,687 square miles. Now, I'm going to demonstrate in a little bit the modest amount of forest area needed for a project on such large scales as I've been thinking. Now, the annual growth rate is important to any plant as anything. The important thing to remember is the sun's got to shine for stuff to grow. The problem with that is Solyndra and other solar panel enthusiasts are coming to understand. The sun doesn't shine all the time. With night, clouds, shading of other plants, and even the tilting of the planet, only about 0.64% of the sun's energy becomes useful to the trees. Now, if when the sun is shining, it radiates about 1,000 watts of energy per square meter, that would be the maximum amount of energy a solar panel, 1 meter wide, 1 meter long, could gather in 1 second. However, it's hard to convert photons to electricity. Returning to our 60,000 people, as a citizen of this community, each individual uses roughly 10,000 watts of electricity every year. Now, I'm leaning on the low side here because theoretically these kind of facilities would run tandem with hydropower. Now, this facility would support individually 60,000 of the hippest cats on this planet with electricity. And that, ladies and gentlemen, is 600 megawatts. Divide those megawatts by the 1,000 watts of your solar constant, and it produces 600 meters square. Now here, located about 47 degrees north, and that dang little darn daylight saving times forces us to multiply by 6, or the hours of sunlight received every day. Of course, this number would be 12 on the equator. The community located at 47 degrees north, that would and are multiplied by 6, we've converted and we've produced 271 square miles. Now, that is 3.6 million meters squared. Here we've inserted and divided by the photosynthetic ceiling, or 0.64%, which is multiplied by 1 over 0.64%. Instead of meters squared, we've got our 271 square miles, or approximately 15 miles by 15 miles. Now, what does this mean? This means the photosynthetic ceiling would allow a 15-mile square area of forest to supply enough biomass to a community of 60,000, to supply electricity to a community of 60,000 indefinitely. And I'm going to speak a little bit on how this could happen. Energy is not power, but power is energy. Does that make sense? Power is energy divided by time. So over time, a renewable energy source, such as the sun, checks off an invisible watt on its little sundial, much more or less the same way the meter on the side of a house meters the house's everyday average energy use. Now, every second, the sun shines more and more of these watts down onto the surface, and they're either absorbed or they're reflected back into the atmosphere. Like the photosynthetic usage, it is hard to convert these invisible photon pyres to dancing electric pyres. On average, an evolved plant species can only convert about 0.64%. So the photosynthetic ceiling then becomes 64 millionths of every 1,000 watts per second. Like charging a battery, the trees store this 6.4 watts of energy every second the sun shines on them, along with CO2, methane, and water vapor while they live. But when they die, they begin gradually decomposing, releasing this 6.4 watts of energy, along with their eventual molecular composition as an atmospheric gas, a liquid compost, or an organic solid material. Or, as in the case of a wire fire, they do it rapidly, which is rapid decomposition. And the only differences here is the time frame and the type of carbon released, which is CO4 as opposed to CO2. So returning back to our 21 meters of volume wood chips and the effect that would have on our forest, a mile is 5,280 feet. Multiply that by 15, and then again by our photosynthetic ceiling, and it produces 710 feet. Now what does this mean? It means that in a certain select area of timberland, if 710 feet, a 710-foot swath was cut for 15 miles south, it would supply the needed biomass to support a community of 60,000 with electricity for 1 full year. Now the next year, another 710-mile swath could be cut to support the power plant for that year. At 710 feet a year, that's 111 years into the future. In all reality, the first swaths that you've cut are ready to be cut again and are way past their disturbance intervals. But this is a healthy forest. What about the bug kill? Funny thing about forests, they grow. They grow remarkably resilient, and they grow fast, as we have been coming to understand. Now, as sections of these bug-killed forests are cut out year by year, flue gas capture and storage could capture these carbons and make it so they didn't get released into the atmosphere, wasted as decomposition gas. Now, a process that is better for the environment than allowing these trees to rot in the forest, let alone allowing millions of them to burn every year. The waste that's produced in this process is ain't radioactive or hazardous. It can be gathered up and taken out to the forest where the biomasses were taken and kind of spread over the ground, much more or less as if nature had burned the area naturally. Ideally, this would be an economic way to stop the bugs and then rehabilitate the forests that they have already killed. Knowing this is theoretically possible with the ideal conditions, what if the conditions aren't so ideal? Say 710 feet of forest land for 15 miles wasn't enough. Let's just double it. Let's make it a quarter mile. That just decreases the forest's photosynthetic ceiling, and instead of harvesting through the swath every 111 years, the harvesters would harvest through it every 60 years. Now, that's problem solved, ladies and gentlemen, for a number of environmental and economic issues. Continuous carbon neutral power to a community of 60,000 people forever sustainable. A quarter mile of fire fuels break for 15 miles in one direction, and in the other direction a forest stand that changes dynamics and ages every quarter mile for 15 miles. Who says these swaths need to be cut in succession or even next to each other? This is an economic way to circle the bug kill and then rehabilitate the forests. Or to keep forests thinned, and either way it's going to theoretically reduce the risk of catastrophic fires and provide an economic way to keep the forest healthy and pristine forever. While, and ladies and gentlemen, this is the most important aspect of this conversation, releasing only those carbons into the atmosphere that Mother Nature would release absent mankind on the planet. Thank you.
Time for questions if you like. questions?
I can't even go Ayn Rand on you, tell you guys how this is all gonna happen. You guys ever seen a Sikorsky? How about the Milwaukee Railroad? The electric locomotive wasn't like an ordinary railroad. I mean, it was an electric, it's like a kind of subway system with the skyline and these power plants placed in the right spot. You've got continental versatility, you've got a relief of foreign oils, and you've got a relief of the fossil fuel generating greenhouse gases that are being released large scale. Now, the reason I'm bringing up the helicopters and stuff is decomposition gas is 50% methane, ladies and gentlemen. Now, it can operate V8 engines. I've seen jet airplanes fly on it. I've seen helicopters fly on it. You can modify a Sikorsky's tank that used for the water dump to hold this syngas in it. And basically with the cargo net, you can lift all your forest materials out of your deep forest where all these hardcore fires and catastrophic fires are starting and gaining intensity and going into the places where we can't get, and they start coming out of those places. This is a way to take those fuels out of the forest, put them on a landing depot for the electric locomotive to transport them down to the biomass reactors. And again, ladies and gentlemen, this is without releasing any more carbons into the atmosphere than Mother Nature would release absent mankind on this planet.
Great.
You answered my question, though, I think, when you said that. So this is all electric.